I suppose I could have also called my talk yet another performance portability talk using acoustic waves as an example. So it's a good theme. We can stick with it. So I could probably skip over the motivation, which is HPC Stencil, since we're all aware of that. The previous speaker already talked about a little bit of our new processor, Scalable, used to be called Skylake. And I'll talk about challenges of porting code to different processors. Again, sticking with the same theme. The solution I'm talking about today is yet another Stencil kernel. And I'll talk about the goals of it, a little bit about how it works. I'll dive into 3 examples of some of the features it provides. And again, performance results on an isotropic 3D FD. Not that that's the only thing it can do, but it's easy to fit on a slide. So again, we all know why we're here. This is my only marketing slide, really. I stole this from marketing. So the Xeon scalable processors used to be called Skylake. We decided to start using these precious metal monikers. Platinum's the most expensive one. Many cases, it's your best performing too, unless you're completely memory bound. You can get up to 28 cores and 8 sockets with that. The next one down would be gold. You can go up to 22 cores and 4 sockets. The one I'm talking about today is a 6148, which happened to be the one that the last speaker used, which has 20 cores and 2 sockets. The instruction set has been expanding over the last few generations. We had AVX and AVX2 on Sandy Bridge and Haswell. That was 256 bits of vectorization. And now with the Knight's Landing, which came out about 3 years ago, and Skylake, we have 512 bits of vectorization. That, of course, will give us 8 double precision or 16 single precision floats. We have twice as many of those, too, so 32 instead of 16 SIMD registers. A new thing was added was masking, so you can easily turn off lanes in the vectorization. There's a few more things here that are a little more specific. Some of them only show up on KNL or Skylake, but they're not really super important for most of Seismic, although we have been able to use the reciprocal instructions to speed up Knight's Landing on some, especially on some staggered grid problems. All right, so again, I think we're all at least slowly being convinced. The previous 2 speakers did part of my job here on convincing about why performance portability is important. A lot of the optimizations require tedious tuning, not just for the stencil you're working with, but every time you move to a new CPU or maybe even a new SKU with a different cache size. A lot of things you try have no benefit, so I guess probably 2/3 of the things I try maybe don't work, at least for a particular CPU or a stencil. When we're trying these things, you often cannot just do them in a simple order. You can't, if you want the best results, you can't just do cache blocking or vectorization, then cache blocking, and so on, without going back and tuning them again. So there's a lot of interplay, and something you thought might not help because you did optimization A before B might help if you do B first and then A. So it's a big space to search. Also, from a kind of a maintenance standpoint, there's some considerations. If you put in a lot of optimizations, like maybe the if-defs we saw earlier, you risk breaking functionality. And now you've got multiple copies of the code that basically do the same thing, and each one of those paths should really be tested every time you touch something. If you put in a bunch of optimizations and now your geoscientist wants to go back and change your stencil, you guys might be butting heads because it's not always easy to go back and change the stencil. And if you've broken it apart and doing various pieces of it in different files or whatnot. The most insidious thing that some of us have run into is that those geoscientists sometimes have the last say in what optimizations are allowed because of the maintenance issue and the readability. So a lot of optimizations, maybe if it's only 10 or 20%, they just don't get in because it's hard to see the original math that was written. As you might guess, we have a solution that we're proposing that hopefully will address a lot of these issues, called yet another stencil kernel. So it's kind of an inside joke at Intel because everybody just says, oh, you're just working on a kernel. So I figured, well, we might as well embrace it. The idea here is that we have an open source software framework. And I call it a framework because it has it's a piece of code that you can build your code on top of. So it's not just a library. And the idea is to rapidly implement kernels for Xeon and Xeon Phi. So we do this by providing a domain-specific language that I'll show an example of in a moment. And then we generate kernel code from that DSL input. So this allows you to separate the functional description from all the optimizations that are applied. So hopefully no more if-defs. Which leads, of course, to easier maintenance and easier changeability of the stencil itself. You can also explore a lot of the trade-offs just from the command line and some simple utilities we provide without ever touching the stencil code itself. And there's some more things that I'll point out as we move along. The output of all this is a library that you can integrate into your code. So again, we start out with a DSL input. And it looks like this different version of PowerPoint is messing with my formatting. That's supposed to be primary, not primar Y input. And then you just type make, and it runs all the stuff in the box on the right. It runs it through our own Stencil compiler and a little loop code generator, generating more C++ code that gets compiled, hopefully with the Intel compiler. That seems to be the best thing we found so far, and no bias. And there's the Y again. The output, again, is a library, and we have a little binary that you can run with that and get performance results right out of the bat, off the bat. And like as I said, we also have some C++ and Python APIs where you can integrate the library in. All right, the YASK has a bunch of features. I'm going to dive down into 3 of those today, and you can play with the other 4, offline. The DSL I already mentioned. Several folks have talked about cache blocking. We have a little automatic tuner that I'll show for that. Vector folding is a somewhat perhaps novel technique of changing the data layout to reduce the memory bandwidth, and I have a few slides on that. We also do things like nested OpenMP, which really helps on the Xeon Phi because you can have 8 threads sharing an L2 cache. Temporal wavefront blocking, if you can put up with doing several time steps at once. We automatically generate software prefetching, and we do the MPI as well. So we've seen this a couple times already this morning. This I'm going to show here is a 16th order acoustic wave, which maybe is maybe twice the order of the early ones, so you can keep that in mind when you see the performance results. So this gives us a 51-point stencil instead of maybe 25, 26, 27, something like that. So on the left, we have the original stencil code, as you might write it out in LaTeX. And then on the right is the implementation in the YASK DSL. So it's pretty compact. The top part up there is just the boilerplate stuff where you declare what the indices are. We're going to have time, X, Y, Z. And then we declare our grids. There's a P grid, which has a time dimension because we're going to be updating that grid. And then there's a constant grid called V. And then I stuck the coefficients in an array. That's not important. But you can see the bottom there, the next, 10, 12 lines is very similar to the math we have on the left. You just build up an equation using overloaded C++ operators. And then there's at the very bottom, there's a equals macro, which means that I'm saying that the equation I just built up is going to be define the value of the next time step. And the compiler then is going to see that equation not as imperative code, but as an abstract syntax tree, and then be able to do things like common sub-expression elimination, things like that, which is not so important for this code, but it's very important for things like TTI. All right, the first performance example I wanted to show is the automatic tuner for the temporal blocking. So this chart shows how the automatic tuner iterates through various sizes of tiling to improve the performance. So again, this is on 2 sockets of a 6148, exactly the same as what was in the last talk. So we ran 162 trials here. This really only takes a few seconds to run. And the bottom 3 lines show that the different sizes of the XYZ dimension of the tile and how it converges over time. And the black line up at the top shows the performance, which started at about 7.6 gigapoints per second. I believe the last talk had something around 5, so we're in the same ballpark. Although, again, I think this one might have been a little higher order. So we started out again at around 7, and at the end we got up to pretty much 10 on this example. The last feature I want to talk about is a thing called vector folding. So to review, first of all, what I call traditional vectorization is. And again, this was touched on in the last talk. So typically, how we vectorize for the CPU is to construct the vector in line with the innermost, the unit stride dimension of the memory layout. So in this case, it would be X. So I'm showing 8 values computed here in X, and the gray dots show the previous iteration. So this is the input on this side then. So as we're moving through the memory, we can see that we have to read lots of vectors for every new vector we're calculating. There's some reuse right here along this axis, but if we look along the Y and Z axes, there's basically 0 reuse. So that means that to do this 25-point stencil, to calculate every vector of outputs requires us to read in 17 new vectors. And on the KNL in the Skylake, a vector is the same as a cache line. So again, this just review for the traditional way we do vectorization. So the idea behind vector folding is that we can do vectorization, by changing the memory layout, we can do vectorization across multiple dimensions. So here I've shown an example where we're vectorizing across 2 dimensions. So that really just means when we get a SIMD register, it's going to have a small block of 2 by 4 elements in it. In this case, those 2 by 4 elements are in the XY plane. So that turns out that it gives us more spatial locality when we're computing a single iteration of the stencil. Another trick we can do is by, again, changing the data layout and our looping structure is that we can iterate in a different direction. And then it turns out that the best way of iterating, the most performant one, is to do it perpendicular to the plane of vectorization. So here I'm showing, that's a button, that I'm iterating in the Z dimension, whereas I vectorized in the X and Y dimension. And that gives us temporal locality as we move from one step to the other. So here I've shown the inputs compared to what we had with traditional vectorization. So we can see that we're loading in a vector here. The blue and the green would be a vector, and that shares data with these other ones here. So we get spatial locality, and then as we move across, we get more temporal locality. If we count up these vectors, we see that we only need to read in 7. So we're still calculating 8 results, but we only had to read in 7 instead of 17 cache lines, which is less than half, of course. The downside of vector folding is it's more complicated. So one thing you have to do is lay out your memory differently if you want it to be efficient. So conceptually, I've shown at the top the logical layout of just a 2D grid. And then say the green is one of the vectors as it's laid out in memory. So you can see, again, to repeat myself, it's no longer a single dimension. And then, so green, orange, these would be vectors. So we still want to lay them out so that all the green ones are together in memory, of course, to get so we can do some single load. The good thing is that YASK encapsulates that behind a class, so you can still just access your grid points, read and write them as you would a normal array through an API. The second difficulty is that now if we want to do an unaligned load, or something analogous to an unaligned load, we can no longer just use the hardware for that. If you look at the elements in the black box, they actually get scattered across memory in this case. So to do that efficiently, we can load these two vectors and then do a permute instruction, which is a new instruction in the AVX 512 to do that very efficiently. We don't have to do a gather. We can do a permute, which you can do in one cycle. And the YASK compiler will generate all that for you. Otherwise, it would be very tedious. All right, so what's the performance of vector folding? What does that buy us? So this is the same 3DFD example, same platform. So the degenerate case of folding is traditional folding again, and that's represented by the one on the left, which is, all 16 values are inline. And I started out here with about 6.3 gigapoints. And then I tried all 15 combinations of vector folding. Some of them are even three-dimensional. The default vector folding is actually 4x4x1, because that usually works pretty well. And it worked pretty well here. But it turns out for this larger stencil that a 2x8x1 is actually the best. And that, again, gave us something about 9.5 here. And by the way, I ran the block size auto-tuner on every one of these points. So the block size would also be tuned for the vector folding. All right, so plug for our friends in London. Our current work, one of our current work is to integrate YASK in with a tool called DeVito, which is a tool for doing finite differences, which even raises the abstraction level yet again. So with YASK, you have to do your on finite difference transformation and type that in. With DeVito, you can just type in your differential equations in SymPy. And then the idea, when they're fully integrated, is that the DeVito compiler will translate the PDEs into finite differences for you, and then talk to YASK, and YASK will generate the final code. Again, there's a website for DeVito, or you can talk to the PI who's sitting in the back. Other things that we're doing is improving the performance of some of the existing features. You are able to calculate different stencils in subdomains, like for boundary conditions. We're improving MPI and temporal blocking. And I'd really like some more code, so if you want to play with YASK and code up a good VTI or a better TTI than the one I have, please do. I'd be happy to take it. So YASK is great. You can download it. Read all these legal disclaimers. Questions? I don't know if the mic is working. The question is, where in the cache hierarchy does vector folding help? So I guess the short answer would be everywhere, because you can certainly it will reduce demands all the way out to memory. So a lot of these kernels are memory bound, especially if you're not doing temporal blocking. So we want to cut down on the number of memory reads. But the overlap works all the way up. In fact, you can get more overlap in the L2 and the L1 and even more register reuse, so all the way into the registers.
Comparison with the Stencil compiler work that's been done at Ohio State?
Question was about the comparison to Ohio State's Stencil compiler. Short answer is no, but we'll be happy to work with somebody from Ohio State or somebody using it offline and compare those.
Let's thank our speaker again.